What we did today was learn how to calculate the estimate of population parameters, specifically population mean. If we go back to the previous example, we had a hypothetical situation where there are 9 babies and their attractive face and an unattractive face, and we timed how many seconds the baby will look at the attractive face and how many seconds the babies will look at the unattractive face. And this is the data, and the mean seconds the babies look at the attractive face was 13. Remember that. And we'd like to know what the population mean would be. We don't know the population mean because we don't have we didn't test the entire population, entire babies in the world. We didn't do that. We just used the 9 babies. But we learned how to calculate the estimate of population mean based on this sample today. Okay, and this is the formula. So basically, what I can forget about this because I don't need this formula to come up with the actual, the estimate of the means. There are 2 kinds of, estimates. One is a point estimate. The other one, the interval estimate. Point estimate is just, same as the sample mean, which is 13. It's not really helpful though. And what we're really interested in is interval estimate. Yeah, here. And how you do that with mean is that one thing is, you can memorize this. But if you want to know why you do this, here's why. Okay, let's think about that. So the previously we had this hypothesis testing. We thought the mean was 10, but the sample mean was 13 here. And the critical value was here. So because it was outside of this margin of error region, we or within the critical region, we rejected our hypothesis, stating that there was some statistically significant effect in this 13 was actual increase because of the effect. That's what we thought. This graph, this histogram here, this is not the actual representation of population distributions, at all, because after doing the hypothesis and the calculation, seems like the 13 was actually the representation of the actual population. In fact, the histogram or distribution distribution of the actual population is, maybe mean is actually 13. It's not the 10. Maybe the population might be distributed like this. That's what this testing leads to. This testing, t-test, initial test, kind of imply that actual population might be distributed like this, with 13 in the center. Of course, that's just based on the sample, so it can't be totally right. So there'll be some margin of error in this too, but that's what we kind of figured from the sample. Let's see. Mean distribution. We want to be certain that the most of the mean sample means should be included in, if we just think this region, for example, if we say means are in this area, then we could probably safely say most of the means of the distribution, sample means would be of the population would be covered. That's the idea. So let's say I want to cover 95%. That's the idea, and so what we're excluding is 2.5% here and a 2.25% here. You know what I'm getting at? This is itself by itself a distribution, like a normal distribution here. We're supposing this is going to be a normal distribution too. This population is normally distributed, with the mean of 13 as a center. That's what we're thinking, maybe mean is 13, that's why it's in the middle and it going like this. But 13 is just a point estimate. Interval estimate would be, we want to have some interval, and interval, how much interval do we want to have? Okay, let's have 90% of the means in this region. So that means we want to cut off the distribution right here and here. So what we want to know is, okay, here, how the distance between this and this, and the distance between here and here. That way we know these two values here, right? That'll be the estimate of, or range, estimate of the range of the means of the population, actual population, And how you do that, unless you know this distance, you can't really tell, right? And how do you know this distance, Actually, we do it. Why is that? Because think about the t distribution, t distribution. It's like 0 is in the middle, and standard deviation is always 1, right? And the critical value is here. Okay, to cover 95%, means, we need to look at the 5%, critical value equals to 0.5 for two-tailed. That way we know these two values. Okay, so two-tail combine and 95% here. Okay. Degree of freedom would be, because there are 9 babies, 9 minus 1 is 8. So here, and two-tailed 0.5 is here. So 2.306, that's the critical value. Okay, so 2.06. This is gonna be a 2.306. This is gonna be a minus 2.306. If you think about the critical value, if you want to include 90% of the population, in other words, sample means, 90% of the means in the population, you should just think about this middle area, 90%, and discard these edges. And if you look at the, if you turn into t distribution, then it should be like this, 0 and here. I mean, and this should be, cutoff point is be 2.306. That's how it is. Okay. Now, if you apply that to the actual population with the population parameters, because mean is 0 here, but in actual population mean is 13, and this is not gonna be, this is not 2.306. If you know the concept of math concept, it's kind of easy. Okay, so what's the relationship between these two? This t distribution and the actual distribution. It's the same shape, same ratio, everything. It's just it's based on the standard deviation is 1. Just 1. This is 1. This is 1. And this distribution is not based on a standard deviation of 1. So if we know the standard deviation of this population, we know the number here, value here. Let's say this is standard deviation of 1, right? So if the actual population has a standard deviation of 2, that means everything is 2 times larger in this. The way it increases and decreases, the way it is spread, it's 2 times larger, more. If the standard deviation is 3, that means how numbers and values change. It's 3 times of this. This is going to be 3 times of this t distribution. If the standard deviation of this is 0.5, that means how values change. It's going to be 0.5 times of this. So that's how you do. And so what's the standard deviation of this? Okay, we know how to do that already. Okay, standard deviation of this is it's like this, right? We don't have this actually, so basically what we need is this. This is what we need. How do we do that? Okay, so standard deviation is population was, okay, there are 9 people, 9 babies, so it's 9. And the sample variance. What was the sample variance? I have to calculate that, but okay. Sum of squares and blah blah blah, and the variance is 9. You got the variance, which is 9, so 9. So in this case it's 1. So actually this and this are exactly identical shape, standard deviation is, or standard error is 1. So that means this value is going to be 1 time larger than this. So it's going to be same actually. So 2.306. It's going to be 3.206, So this is going to be 15.306 here. So it's 10.694, something like that, right? Okay, estimate is 10.694 to 15.306. Well, actually, how you want to say is mu, estimated mu is plus 13. If you don't want to calculate, 13 plus minus, you can just say 2.306. That's how you can do it.